السلام عليكم ورحمة الله وبركاته طلاب المرحلة الأولى Linear Algebra 2 First Level Lecture 14. The subject for today is orthogonality in Rn times 1. Orthogonality mean تعامد in Arabic. Definition: let VW belongs to Rn times 1, then we say that V and W are orthogonal if and only if V dot W equal to 0. If the inner product, if the dot product VW equals 0, then we say that V and W are orthogonal. This definition. Now this is example. Let V equal 1, 2, 3. Describe the set of all vectors or are orthogonal to V. This is question. Describe the set of all vectors which are orthogonal to V. Solution: let W equal x, y, z be an arbitrary vector in Rn times 1. 0 is equal to V dot W, and this is V, 1, 2, 3. This is V, and this is W equal x, y, z. This is equal x plus 2y plus 3z. This is equal 0. So any vector satisfy this equation will be orthogonal to V, 1, 2, 3. Look like if x equal minus 2, here 2, if x 2 and y minus 1, and this is 0, this is will be orthogonal to V. This vector will be orthogonal to V. Now, proposition: Pythagorean theorem in n dimensions. Pythagorean theorem: if x, y belongs to Rn times 1 are orthogonal, this is two vectors are orthogonal, that means the dot product between them equal to 0 vectors, then norm 2 plus norm x square plus norm y square is equal to x norm x plus y square. Moreover, if x 1, 2 until x sub k are orthogonal, then norm x1 square plus norm x2 square plus blah blah x sub k square. This is will be equal to x1 plus x2 and so on to x sub k square. And the proof is easy. If we take the x norm x plus y square, this is by definition of norm equal x plus y dot product x plus y, so this is the same, and this is move here and here, x dot x plus x dot y plus y dot x plus y dot y, and here x dot y equals 0 because x is orthogonal, x y are orthogonal, so x dot y by definition equals 0 and y dot x also equal to 0. So this is x dot x is equal to norm x square plus y dot y is equal to y square, norm y square. This is page number 1. And the proposition: the 0 vector is orthogonal to all vectors in Rn times 1. Let x, that means any vector dot product with 0 will be the result will be 0. Let x belongs to R times n times 1, not 2 times 0 equals 0. We know that. Thus, x dot 0 dot x is equal to 2 dot 0 dot x, and this is equal to 2 0 dot x. So here 0 dot x equal to 0 dot x, so 0 dot x equal to, which implies that x dot 0 dot x equal to 0 for all x belongs to Rn times 1. And now we take definition of orthogonal set. The first definition, this definition is orthogonal vectors, and here is orthogonal set. A set S of vectors in Rn times 1 is orthogonal. This set will be orthogonal if and only if every pair that means زوج, every pair of vectors in R in the set S is orthogonal. The set S is orthogonal. Every pair in the set S is orthogonal, then we say that this set S is orthogonal. If S is orthogonal and all vectors in S have length 1, all vectors in S have length 1, then we say that S is orthonormal. Then we say that S is orthonormal. Take this as example. Let S is equal to 1, 1, 0 and 1 minus 1, 0, and here 0, 0, 1, and this is dot product. We show that this set is orthogonal. We will show that this set is orthogonal. How can do that? Dot product for all its vectors will be 0. This vectors with this 1, 1, 0 dot product 1 minus 1, 0. This 1 times 1 equal 1. 1 minus times 1 minus times 1 times 1 minus 1 minus 1, and 0 times 0 will be 0. This is will be 0, and this is 1, 1, 0 with this vector now 0, 0, 1. 1 times 0, 0, 1 times 0, 0, 0 times 1 will be 0, so this is also equal to 0. And the last one, 1 minus 1, 0 with 0, 0, 1 also will be 0. So S is orthogonal. S is orthogonal because every pair of its vectors, the dot product between them equals 0. Now we want to show that S is not orthonormal. If S orthonormal by definition should be the norm of all vectors is 1. Norm of all vectors is 1. Now we take this is 1, 1, 0. This is 1 square plus 1 square plus 0 square. This is equal root of 2. This is not equal to 1. So S is not orthonormal. Therefore, S is not orthonormal. This is example about orthogonal set. This is example about orthogonal set. Now we take extended Pythagorean formula, proposition, extended Pythagorean theorem in n dimension. This state if x times 1, x times 2 until x times k are orthogonal, then norm x times 1 square plus norm x times 2 square until norm x times sub k square is equal to norm x1 plus x2 plus x sub k square. Proof non x1 plus x2 plus x3 until x sub k, this is equal to by Pythagorean formula is equal to x1 square plus x2 until plus x sub k square, because this is by above proposition. This is proposition. This is a proposition. We use this proposition now, this, and make this just one vector and this one vector, so this will be satisfied. And continuing in this way until we obtain Pythagorean theorem for k orthogonal vectors. And this is finished proof. I think it is clear. Now this proposition, another proposition. If S is equal to V1, V2 until Vn subset of Rn times 1, there is no, just subset, is an orthogonal set of non-zero vectors, then S is linearly independent. If S is orthogonal set, if S is orthogonal set of non-zero vectors, then S is linearly independent. Proof. Suppose C1, C2 until C sub k belongs to real numbers, such that C1 V1 plus C2 V2 until Cn Vn equal to 0. So sorry, Ck Vk. So sorry, Ck Vk take dot product of both sides with respect to Vj belongs to S, any vector in S. and this all vectors of S, v1, v2 until vk. This is all vectors of S, and this is anyone from these vectors, of course. And if we take the dot product with this set, this will be C1 v1 dot vj plus C2 v2 dot vj, and this is so on until ck vk dot vj, and this is equal 0 dot vj. Also this is equal to 0. Notice that all terms above vanish by orthogonality, except for one terms. This is page number 3. Except for one term, and we are left with Cj Vj dot product Vj equal to 0. Why all of them will be 0? Because this set is orthogonal. S is orthogonal. Any vector with all others will be 0. Dot product with all others. So this is will be 0. This is Vj. Vj anyone. Maybe V1, maybe V2, maybe Vk until Vk. One of these V1 to Vk, we choose Vj and dot product with all of them. So this is V1 0. This is V2 0 because this is orthogonal with all of them. Just one, not 0. Which one? Will be Vj. Vj with itself will be not 0. Vj dot Vj will be just this, will be not 0. However, Vj is not equal to 0 because this set is non-zero vectors. The set of S non-zero vectors. This is also condition here. Thus, if Vj not 0, so Vj dot Vj also is not equal to 0. That means, and it follows we can divide it by we can divide by the non-zero scalar Vj dot Vj for this here divided by Vj dot Vj will be leaving Cj is equal to 0, but J was arbitrary. Hence, C1 equal C2 equal until Ck, this is equal 0, and hence S is linearly independent. And this is finish the proof of proposition. Now take definition. Let A, this is vector, is not equal to 0, B another vector, B vectors, then we define this is definition. Let A not 0 be two vectors, then we define projection A on B is equal to B dot A times B dot A hat where A hat is equal to 1 over norm A times A. Moreover, the length of a projection A B is called component of B in the A direction. In the A direction, and is denoted comp A B here is equal to norm, this length, projection A of B this is definition of projection. And this is example. Let A is equal to 2, 1, this vector, and B is equal to 2, 4, 6. And if we find the projection A of B, this is equal to, by this way, B dot product with A 1 over norm A times A with 1 norm A. Because there's here A hat and here A hat. And if we substitute here, this will be equal to B. Of course, we can do it look like this. 2 to 1 dot 1 over norm A. Norm A here square 449. This will be 1/3, and a, this is, sorry, here a 26 root of 26. This norm a, not no, true, this is a 3. Okay, of course this is a 3 because this is a. Norm a is 2, and this is b here 2, 4, 6. This is b, and this is a here. Norm a is 1/3, and a is 2, 2, 1, and after that 1/3. Also a 1, 2, 2, 1. This is will be equal to here this is will be equal to here, move here, and here 1/3, 2/3. This is will be a single point, 4/3, and here plus 8/3, and here plus 6/3. This is times here 2/3, move this here, and 2/3 and 1/3, and this is will be equal to this will be equal here 18/3 will be 6. This is will be equal 6, and move 6 here. This will be 4 because this is 6 times 2 will be 12/3, 4, and here 6 times 2, 12/3, also 4, and here 6, 2. So this is projection a direction, the projection of b in direction of a will be equal to 4, 4, 2. And this is example, and this is page number 4. This is page number 4. And now take another subject. I think this is enough for today. So the next subject will be take Gram-Schmidt process. Thank you very much. Goodbye.